calculation.
The four corners.
Correct. And then after we have for each direction and each floor, when we have the responses due to the three directions of the earthquake, then we apply the SRS method to find the final design spectrum, as shown in the last.
So you envelope the four corners to get a representative spectrum for the whole floor.
Correct. X, Y,
One
and Z.
direction, or due to the excitation in one direction, and then you SRSS for contribution
Correct.
in the different directions, but always in the same direction of the spot.
Of course, yes.
Same thing for walls.
For the walls, we have oscillators for out of plane, and basically we use those for the flexible walls. But for the rigid walls, the full spectrum works. The next slide, 28. Now, I just want to show what is the effect of this correction. They are fairly minor for translations, because what we used before that, we didn't really make mistakes, or we are very close. For the vertical directions, and this triggered us to make the change. We saw that by applying the correct method, we obtain vertical spectra which is slightly higher than what we used to have before. The next slide. Now I want to talk a little bit about the error we corrected for the site instability of fire water service complex. Basically, the fire water service complex is supported by concrete field, and then we have shear keys which are embedded in the concrete field. Around the foundation, we have a soil. So basically, in the calculations we did in the previous FSAT, we calculated the distant force coming from that soil around the foundation, and using the assumption that we will have a passive resistance engaged. Basically, on the next slide, as I discussed, due to the high stiffness of the concrete, we won't see any types of deformations that will be sufficient to engage passive resistance. So basically, we corrected for this error. We saw how much effect that will have on our result. Basically, the numbers didn't change because the resistance provided by that soil around the foundation is very small. But we corrected the description and the FSAR to say that we neglected the contribution of the soil around the foundation.
Go back to the previous slide. So I think we asked this before, right? But I just wanted to perhaps talk a couple of things. Meaning what? The purpose of the shear is lower the shear point, the failure plane, to under the shear.
Correct.
Right. So the base hypothesis or the minimum factor on a shear plane that's right under the shear. So the shear has to be strong enough to be able to do that. That's what you...
Yes, in the RI question, basically we check the loads that we have in the shear keys, and they are lower, those demands are lower than what the shear keys were designed for in the standard design.
Okay.
For the plane below, we are coming in the full concrete, so we can rely on the full strength of the shear strength of the full concrete. We did calculation, but it's not documented. But we'll talk in the RI research about that.
So basically, what you're saying is that you're ignoring any passive resistance of the fill material that's like beyond wall, right?
Correct. But it wasn't clearly, so basically the language was changed.
So now we're going to the, oh, okay, so that was, Ruben just summarized the changes that are in the letter we sent yesterday. So now what we were going to do is go through the draft RAIs and our draft proposed responses. Do you guys have any questions before we do that? Perry, do you want to take a, what time is it? Yeah, okay, 9:52, so we can keep going for a while?
Does anyone need to break virtually?
Well, and people are, it's okay to go to the restrooms if anyone is right out of it. Okay. All right, so now Alidad's going from, Hashremi from Bechtel's going to go through the 371 related REIs, okay, which I think was 7520, yeah.
So what we're doing here is first describe what you understand from the REI question, and then show you our proposed methodology into answering them. And start from REI 7520, and we number the questions sequentially, A through whatever letter that comes in. So
before you start with that, Alidad, Ross made copies so y'all could keep up if you want to, you know, that and apply the alpha numbers. So does everyone have a copy of that if they'd like one? Oh, okay, great.
Okay.
All right, so, Slide, you okay?
Yeah.
Okay. All right.
So the first REI question was asking us to clarify whether we're using backfill materials, whether we're including the effects of backfill material, both granular and concrete fill, in the development of FAIRS and PBSRF. And if we are doing that, how we are including that. So in response, we point out that the backfill material is not included in the FAIRS calculation and the PBSRF calculation. And the reason for it is that the backfill has a very limited extent compared to the foundation dimensions of the building.
Can you elaborate on that? Like,
Sure.
From what I saw in the application, there's a plan view, right? And it's not clear to me exactly how much is going to be excavated and how much is going to be backfilled. So when you're saying that the backfill has limited lateral extent,
So
how do I know that?
maybe people from DH can answer that question with numbers better. What I understand is that it's very limited.
I mean, roughly
It's about 3 meters.
10 feet.
You're just excavating a little tiny thing around the power block structure, and then beyond that, what is there like food wall or something?
There's a bulkhead that's been placed around the structure for excavation and construction.
Oh. That document
There is excavation plan drawings. But please know that we have not that much soil. It's not the whole building is in soil. We have rock, and then we have soil.
But Larry, you're talking about lateral extent, right?
Right, so we don't have to go too far.
Beyond, like, size of, like, small lateral structure, you're saying it's only 3 meters? So the excavation is not very big, but it's lateral extent.
Right.
Dan, Howard, are you still on the phone?
I am.
If you have time, could you, Dan's from the floor, could you look, I think it's in 254, the excavation plan.
Excavation drawing? Yeah, I'll look it up, Gina.
And then if you give me the number, perhaps I can pull it up at a break just to show, you could show the NRC, all right? You understand what, Dan, I'm not sure if you could hear, did you understand what was being asked?
Yeah, it's looking for the sizes of the excavations relative to the buildings, right?
Exactly, yeah. Thank you, Dan.
Yeah, I have a lot of fun. If I can, answer this question, you can calculate foundation response factor in basically 2 different ways. One takes into account the upper part of the profile. Another is considering pressure outcome. And you choose the first approach. Now, shouldn't this first approach create a situation base? Because if you ignore this upper part and treat it as an outgrowth, you don't have this.
Right. So let me state that differently.
That's why, but you have goals.
We have exactly. We have both. So we have a surge that is corresponding to the full soil column, and we have a surge that corresponds to the partial soil column, which doesn't have the saprolite on the top, doesn't have the soil on the top, but it has the.
Which is always at the top.
Well, let's get to that. That's also a question. Basically, those we are considering both, and the reason we are doing that is that we want to be consistent with the SSI analysis that follows. So that's the whole issue. The site response analysis has to be consistent with the SSI analysis. So our justification, obviously the most important point, is that the backfill has very limited lateral extent. That's why we don't include it in the pre-field calculation. SIRS and PBSRS are calculated in the in-situ material at free fields, meaning away from the structure, and consistent with ISG 17 and NEI white paper. The FIRS and PBSRS calculations are consistent, very importantly, with the SSI analysis and the site material that SSI analysis used in its free field module for that. And finally, that the backfill effect will be explicitly evaluated as part of the SSI analysis. So any effects that backfill material that we're not including in the free field will be addressed elsewhere. Separately.
A couple of things perhaps to clarify.
Yes.
So when we're talking about backfill material, I'm thinking basically the granular backfill. Why am I saying that? Because if you have a fault, if you have like the structure partially embedded into the wall, so you have the first down here, you have the top of the ground down here, and then you have this column of backfill, relatively soft, granular backfill material. You like two PBS way at the top. That's going to have the effect of the relatively soft material, or it's going to give you a relatively high PBS. Now, in the NEI approach, where you have to involve FIRS, computed FIRS, all the way up to the surface and make sure that it envelopes the PBSRS. The bigger the PBSRS, the harder it is for you to demonstrate that envelope. So that's why the concern is that if you're not considering the relatively soft material, the impact of the PBSRS is right, and therefore indirectly on the SSI, the modified, I don't know what you call it, a hand. Right?
So let me clarify on that point. The PBSRS is calculated consistent with FIRS, in the same soil column, and we'll get to that question in a couple of slides. What I want to point out is that when you're doing the NEI check, what you want to do is that you basically, and I'll talk to this point later on, you want to make sure that your probabilistic approach in response analysis is compatible with the deterministic approach of SSI analysis. So in order to do that, you would apply the FIRS in the soil profiles that you want to use in the SSI analysis, and you calculate the corresponding motion on the surface. So whatever amplification that was in that soft material that caused your PBSRS to be high should also cause your amplified response from first to surface in those three profiles also be high on the surface. So that effect of soft material is on both sides of that equation. However,
what that tells me is that both should have been done with the backfill, right?
So that depends on your SSI analysis portion. So if you in your SSI analysis you're not including the soft soil on the top, and you have good reasons for it, then you don't need to include that portion of the NEI check. You don't need to check that the surface response is adequate because it's not transmitted to a structure. It doesn't exist in the SSI model. So that's the connection between them. And if you don't mind, we'll get to it in a couple of slides, and we can talk some more about it. Okay. The next RI question was asking us about the methodology for determining the strain-compatible lower bound depth estimate and upper bound soil profiles such that there are consistency pairs for each seismic category 1 structure. And in that, the question was pointing out correctly that we do the search response analysis at 10-4 and 10-5, not at the first elevation, and how do we arrive to the strain-compatible properties which are consistent now with first, which is somewhere in between. The question was also asking us for the companion profiles. These are the profiles now including the backfill properties, meaning the engineered fill and the concrete fill. And how did we calculate the strain-compatible properties for those? It was asking us to explain how they are used, how they are developed, clarify if a full probabilistic site response analysis was repeated to come up with those properties. And also a couple of more editorial questions was clarify the term VS third, and also clarify the groundwater table used in the SSI profile. And if you can go to the next slide. In our response, we will provide all the detailed descriptions for our methodology to come up with the strain-compatible properties that are consistent with first. Essentially, we are using the same interpolation that was done between 10-4 and 10-5, etc., to come up with strain-compatible properties for first, and that is done consistently. And we'll provide those details. For the companion profiles, these are explicitly included as finite elements in the SSI model. So that's the use of them to evaluate the field effects in the both range.
That's not documented in the 17. That talks about the concrete.
Right. So it's a sensitivity study that comes in, and we'll talk about it towards the end of today's presentation. But the concrete part is included, and the physical. Right.
Right now, the licensing basis is that it's a partially embedded structure, and that's how the SSI analyses were performed for RBFB and CB, right? But we'll get, you know.
The concrete field is treated as part of the structure.
It's included in the SSI model explicitly. Yes.
Model as a structure.
Part of the SSI model of the structure is not the
It's part of it's explicitly as finite elements included in the SSI.
Yeah, that's a structure.
It's a house model. The house model.
Well, that's structure. Yeah, but that's what it is. I mean, you can be a structure, can be soil, right?
Well, from my soul point of view, it's not part of the structure.
Right.
Right. For your analytical model, it's part of the structure part that you include.
But it is treated as a part of the structure.
Correct.
That's how you treat it. What about
That's good.
actually also treated as part of the structure?
Yes, in the sensitivity
Okay,
study.
that's what that one. Yeah.
That's not documented in the 17.
No. No, we talk days ago.
Because the way you did the site response analysis, I think you the basis the lateral standards were low in that, right? So I think, but then you include the whatever the executed portion that might be range that you included as part of the structural model.
That's
So all that is included as part of the structural model in the modeling consistent. And that's what's important.
I think the main thing for us was that we were confused when we read 372 and we read 371 and we read 352 and 351. It just didn't match. So we were confused. But anyway.
You know, 1 minute I just want to make sure, only couple of days you do something like partial embedded.
Yes, exactly.
You want to bring it out today?
Yes, we are.
Okay, I just want to make sure these are the guys
Right.
who have to make decisions, not me.
Right, and this is exactly what it really.
What's the difference between companion profile and the regular profile and
So the companion profiles are the regular profiles are the in situ material. They are
I understand the regular profile.
farther from that 3 meters, right? But we still, because we want to include that 3 meter soil in our sensitivity
You want to
study.
include the 3 meter defined field as a part of the.
That's right.
No. I thought that was the original model. I thought the companion model didn't have any of the property market.
Right.
Let me finish now. Your FIR and the PSRF was computed using the site cost, neglecting the site field, the lender letter of intent. Okay. And then you develop 3 profiles based on, consistent with the FIR and PSRF.
For the site.
Okay. For that analysis, we would model the site field as a part of a structure. Isn't that how?
So there are 2 analyses. One is that it's fully embedded. One is that the partially embedded. For fully embedded analysis, you would include the backfill as part of the structure.
But that is not in the FSAR today.
Yeah. I mean, what's the difference between that and the partial?
The partially embedded analysis only includes the rock, embedment in rock. The fully embedded analysis takes it all the way to the surface.
Oh, okay. So okay, you consider the partial
Right.
surface.
It
What
still has,
below is the rock, right? That's below the foundation, right?
no, on the sides of the foundation, the rock comes up. Right.
So you only consider the rock portion of the embedment. That's what I consider.
Exactly.
You don't consider the partial embedment.
Exactly.
Okay. And for partial embedded case, you did not model the backfill.
Right. The engineers did.
Okay. And you also did the fully embedded, all the way back all the way up to resurface. So you include the backfill as a part of the structural.
Right. And that's the purpose of companion profiles, to come up with strain compatible properties for that portion of the backfill that will be included in there.
Can I paraphrase what you just said to make sure that I
Sure.
understand correctly? So for the SSI model that considers the effect of full investment, which is not documented in 272, but you're doing it as a separate study, right?
Right.
Okay. That site model considers the in-situ saprolite layers, in-situ zone 3 rock, zone 3 zone 4 rock.
I need to see all those wide.
Down to 9,200.
Okay. Structure model, the house model, considers part of the excavated volume, considers brick finite elements that represent the granular backfill material. So those would have to be represented using strain iterated properties that you documented in 2001, which we were trying to figure out where to use those. Okay. Then you also use brick elements that represent concrete fill, and of course those are linear, so that we call that. Those are documented also in 2001 in those same tables. And then the rest is just the actual structure, walls and stakes. Do I get that right?
That's exactly.
Okay.
You understand?
Okay.
There are plots also.
Okay.
So let me just, so basically that's.
Sorry, one last question. How did you come up with those strain degrees?
So exactly. So as part of this, part C of this response, we clarify that yes, we did a full probabilistic site response analysis to specifically calculate those factors. So exactly what we did for the in situ, we repeated for a soil column that includes the backfill and the concrete fill, and we calculated compatible properties. So it was done as rigorously as your pre-field site in situ properties.
We didn't state that, though.
That's not confusing a little bit.
But that's what analysis is used only for developing properties for backfill.
Only for backfill. Right. That's
Not for another firm.
not for the first, right? We will also clarify that the term VS FAIRS refers to the best estimate strain compatible VS, which corresponds to the FAIRS level of input motion. And this clarification we will add to the FSAR. As part of the RAI response, we'll also clarify the groundwater table used for SSI profiles and speak to its effects in how we calculate the T-wave velocity. And also there was a typo that you pointed out that we were saying shear wave velocity instead of T-wave velocity for 4,800 feet per second, and that typo is incorrect.
Where is the elevation?
In section 254, we provide that generically, I think, and for buildings specifically. But in the tables that we have, the SSI profiles, we don't explicitly state that there. So that's what we show you exactly where we consider the groundwater table for each profile and what its effects on.
Historic data, is it the maximum possible? Is it feet from the surface?
Right. I don't know, but
the assumption that you took for the SSI is consistent
yes.
with information in 2.5.
Yes.
That's all enough to say is
It's a nominal.
All right.
Okay. Can we move to the next one?
I guess just on water table, the groundwater analysis, it did maximize groundwater. There's lots of iterations to look at reasonable maximum.
Okay. I guess.
The next question was asking us about the Poisson's ratio values in table 254208 in relation to the Poisson's ratio values used for the development of SSI analysis profiles. It's also asking us to provide specific Poisson's ratio values used in the development of T-wave velocity profiles in tables 371, 201, 206, and the technical justification. Also, it was asking us to identify in our SSI profiles what is the soil and rock material assumed for each layer in these SSAR tables. So in response, we will point out that the values in table in 254 section, those are the best estimate values generated to the site. These values are however, the values that we used in the SSI profiles, these are developed consistent with the way that we developed the shear wave velocity profiles for each one of the buildings. And so these are either boring specific or depth range specific, depending on the type of material that we use. We'll provide those specific Poisson's ratio values in our RI response, and we'll provide the justification for it as part of the response.
You measure VP and GS.
Right.
So from there you develop Poisson's ratio.
Exactly. So that's what when we say boring specific, that's where it comes from, basically.
Again, in certain areas, if it's true, Poisson's ratio is too close to 0.5, there you limit.
Right. We limit it to 0.48.
And then you back out with whatever that.
Whatever the corresponding T-wave velocity.
That makes sense.
Where I was a little bit confused was if the values that are given in the table 254208, because that table has read it said that there were small strain Poisson's ratios and large strain Poisson's ratios. So it seemed to me that there was some sort of intent to large strain Poisson's ratios with a strain iterated profile. Was that the intent? I just was confused. Why do you have two sets of values?
I'll let John Davies. Is John on the phone?
Yeah, I'm on the phone. Basically, the large and small strain values are only for the two soils. One is structural fill, and the other is the type 2B saprolite. The Poisson's ratios are the same for high and low strain for all the other materials. And in fact, this is an attempt to explain some of the higher